Hi, hello, welcome everyone to Make It Academy Learning. Today we're going to do some revision for the first chapter. I call it for Solid Mechanics 2, where here we're going to recap what we have learned in combined loadings. Combined loading is the last chapter for Solid Mechanics 1, where we learn on how to draw the stress element for a specific location prior to the calculation of a stress and strain transformation. That is the first chapter for Solid Mechanics 1, Solid Mechanics 2. So here you can see on the screen right now, this is a mind map of stresses. I'm going to divide into two. There are on the right hand side over here. You can see this is the symbol of sigma for normal stresses, and on the other side, on the left hand side, we have transverse shear stresses. There are two of each. We have normal stresses for, first of all, you guys have seen that this is the first concept of stress that's perhaps the simplest one. We have sigma equivalent to P over A. P for point load. A is the area divided by the area of the structure, the strut or the beams, and probably it can be represented by the simplest one. If you have a cylinder, so the forces pulling this divided by the area of point load P, that is the pulling or pull or compress, regardless the line of force magnitude, the line of force. If it is divided by the area, that is the normal stress that we know of. That is the first type of stress that we covered previously in combined loadings. And the second one is, I'll call it, this is the most selfish equation in solid mechanics. We have sigma equivalent to my over I for bending, bending stress. This is normal stress. This is bending, and here we have m for moment. Y is the distance from the natural axis to the point of interest for you to calculate, and in fact we have negative symbol in here for bending stress, where negative represented in the pure bending. We have according to the derivation, negative refers to the contraction of the upper part. If you can imagine, if you have a beam, prismatic beam, so this is the natural axis for the beam right now, and the derivation that this equation came about is when we have the original view from this side of the beam, from the side of the beam. This is before, and after it becomes, this is what it looks like after the bending, when moment exerted on both sides of the beam, of the prismatic beam. So at the end, it looks like the negative came from the contraction, because the shortening effect we have on this side becomes negative, because the structure technically shortened due to the bending occurred on the beam. Now, the equation affiliated with this chapter for normal stresses. First of all, we have this normal stress, the simplest one, and the other one we have sigma equivalent to negative my over I for bending stress. Now let's move to the shear part of the stresses. We've got two taus over here on the left hand side. One for torsion, if you can recall, this is from the chapter torsion. This is a torsion where we know tau is equivalent to the representation of shear in this chapter. We call this tau equivalent to Tr over J. So Tr over J, or rho replacing the R, rho representing the outermost radius. Some textbooks is using tau equivalent to Tc over Jc is for the farthest distance or the outer radius of a shaft. Typically, rotation, torsion can be in terms of not simply a shaft. It could be rectangular beam, but for ease of understanding, the derivation was coming from the shaft where we have right hand rule. If you have a shaft like so, and these usually represented by a double tip arrow to represent the torque, right? The torque is just similar to bending. The unit is still Newton meter, but the nature of these, we need to follow right hand rule, where wherever your thumb, right, this is your hand, right hand rule says that your thumb going to show the direction of the torsion, and your fingers, the wrapping of your fingers is in this case the rotation of the direction of the rotation of the torsion of the torque in this type of torsion, this type of stress in torsion is that way, which is looking at from this view, it is counterclockwise. So Tr over J is the equation that we need to understand in terms of usage, and of course J, the polar moment of inertia. One should remember also J, the formula for J, polar moment of inertia, is pi r to the power of 4 over 2. This is the general formula for polar moment of inertia. And well, perhaps it is important to know as well the moment of inertia, or the second moment of area, represented by I over here. I is equivalent to, it's just the cousin of J. I is equivalent to pi r to the power of 4 over 4, or if you remember this in terms of not radius but diameter, by d to the power of 4 over 64. Same goes to J. J can be represented in diameter, which is by d to the power of 4 over 32. And this is, last but not least, the fourth type of stress. We have for this type we have I think I can say this is the most complex stresses that we have in overall concept of stresses. We have transverse shear, where you need to spend a good deal of time of doing the revisions on this in part because the understanding now you need to view the structure in three-dimensional. I think that is one of the most students found it is difficult to comprehend, but whatever it is, the calculation is pretty much simple. The fourth one we have over here, I'm going to list down the equation of what this is actually tau equivalent to VQ over IT. Yeah, this is a mouthful in terms of terms that we need to use. It was like pretty much the combination of bending stresses and everything that you have over here. We have V for shear force, Q is the first moment of area, right? And you have I borrowed from the previous concept of bending, and T is the thickness of the prismatic beam that we consider. So probably it is easier for me if we can see this beam right now. Again, it is a prismatic beam, and of course it has its own neutral axis over here, tau equivalent to VQ over IT. Q itself is the first moment of area, A prime times by Y bar prime. That is a formula for Q. Q is the, remember, this is the first moment of area. T is just the thickness of the prismatic beam measured from the at the bottom of the thickness of the beam parallel to neutral axis, and V is just the coming from of course the V is actually the representation of shear force. But for if you can remember, specifically in this chapter, for shear force we need to calculate the maximum out of what? This is shear force diagram, and together with shear force diagram, if you still remember, that we have also bending moment diagram. The maximum, that is what engineers are interested to know in order to design their structure. So we need to have so if we have T tau max, so we also need to be maximum as well. So there is a formula that we have, A prime times by Y bar prime. That is the formula, and the transverse shear, the shape of the stress profile will be it looks like a parabolic in this kind of volume. Maximum going to occur along the line of neutral axis, and the minimum going to occur at the we call that skins, or the top and the bottom of the prismatic beam. The outer fiber, that is the word they use in some textbook. This is opposite with bending stress, that we have the maximum for bending stress. If you can draw it in three-dimensional, it is maximum at the outer fiber. What does it mean by outer fiber? Is this location over here, right? The maximum means that the highest value, one in compression, the upper part is in compression, and the bottom part will be in tension, and there is where the concept of bending stress gives the shape the stress profile, which is opposite to, I can say it is opposite to this sigma transverse shear and bending stress. They are equal in terms of magnitude, in terms of the stress, but the nature of the stress itself is pretty much different. And I hope this 15-minute video can help you in recalling whatever we have in combined loadings. That is the last chapter, but we're going to begin with this chapter with this revision. I hope you enjoy this 15 minutes video, and to begin the part 2 of cell mechanics, and stay tuned to the next video. Thank you very much.